Hi guys, I'll be talking about screen space ambient occlusion here. Sort of like I'll be doing sort of like a quick, as fast as possible, run down speed run of it, and skipping a lot of the details. The idea is to get you guys interested in starting this, and sort of one single example of something cool that shaders can do. Okay, overview. Ambient occlusion is an effect that tries to model ambient light a little better than a single constant value. Sort of the old 2004 model of ambient lighting is you add a constant number, right? You add a constant color value to your diffuse lighting and call that it. But light in the real world doesn't sort of behave like that. Ambient light in the real world does actually exist, but if there were to be ambient light in the real world, a better approximation is to attempt to model the ambient light getting into spots that are easily ambient light hitting spots that are easy to hit versus ambient light hitting spots that are very hard to hit. And SSAO is a shader effect that tries to estimate AO in real time. In real time means it's dynamic. When the scene changes, the ambient occlusion adapts to it. And this was first popularized by Crisis. Some guy, Crytek, came up with it. And since then, everybody's jumped on the bandwagon. So that's what ambient occlusion looks like a few generations before. You used to bake it in your favorite model renderer, 3ds Max or whatever, and you store it in a texture. Actually, they wouldn't store it actually in the texture as itself. They'll just bake it, and then they just pre-multiply that into the texture map of the model itself. Right? So this is what the game saves. Just the ambient occlusion multiplied with the diffuse color, and they just store that in the texture. What is ambient occlusion? So light in the real world actually bounces around. It doesn't just hit the surface and reflect off completely. Well, it does, but then that light that reflects also reflects again. So everything that gets hit by light actually becomes a little light source itself. You think about this sort of same analogy as moonlight. The moon doesn't actually give off any light, but it gets lit by the sun. And the light gets hit by the sun and then bounces back onto Earth. But on a much smaller scale, right? So everything you can see is actually a little light source in itself. So light actually sort of bounces around everywhere. And what ambient occlusion tries to model is light bouncing from very distant sources, say the sky, right? Coming onto your object. And on the surface of the object, if the object is just a flat surface, then the skylight just goes boom onto it. But if there's a crack on the surface, so it's like a surface like a canyon in the middle, then ambient skylight finds it very hard to bounce into that. Right? It sort of has to bounce into the little crack and sort of have to bounce all the way down to the bottom to the crack. So those areas have darker ambient light, and that's what ambient occlusion is. Expressed in math terms, it's how much of the sky can every point see. For your entire scene or entire object, for every point on the surface of the object, how much of the sky can you see? If you're at the bottom of a cave, then you pretty much can't see the sky very much at all. Just this silver, little tiny bit of sky, right? If you're at the bottom of like Manhattan or something, you don't see a lot of sky. But if you're just on a flat ground, there's sky all around you. And one way to model that is you get every point, you look at every point, you fire rays out from this point in every single direction, and how much of those rays get occluded is how much ambient occlusion it is. So when a ray hits a wall, right, boom, oh, there's a wall there, I'm inside a wall. So you found an occluder. And also don't care about occluders behind you, because occluders behind you, like something there can't exactly block sunlight through here, in this direction, right? Like there's nothing here that can block sunlight coming from here, right? So you only care about this hemisphere in front of this, so it's in the direction of normal. And that's what ambient occlusion looks like on a model. So that's what diffuse lighting plus dumb ambient constant factor looks like. And that's what the two multiplied together looks like. So it's a subtle effect, but it makes a big difference. It gives much more information about the shape.
Especially in the face.
Yeah, especially in the areas in which diffuse light doesn't hit. Like the other side of diffuse light. And that's what baked ambient occlusion looks like. So that's what like render farm, 5 hours, ray tracing, bouncing everywhere, the true ambient occlusion looks like. So, I know a lot of you guys are coming from Unity, so this is sort of the entire picture of the graphics pipeline from like a very simple version. The app, you can replace that with Unity, right? So you make objects in Unity, graphics objects, 2D ones, and then Unity from that generates a bunch of geometry, textures, and lighting stuff, and a bunch of other stuff. And it passes all that stuff into Open GL, right? Which is an API, which is a software API. And this Open GL API gets implemented by the graphics drivers. And then what happens after that is sort of magic to a lot of people, right? It gets sent to Open GL and then blah, 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 something, GPU, something, and it comes out on the screen, right? So that's what actually, this is a simple version of what actually happens. The drivers run your geometry through the vertex shader, turns your geometry, turns your triangles. So the geometry shader places the triangles in the right way in your camera. And once that's done, it turns that geometry into pixels on the screen. And those pixels now get lighted. You have to figure out what color those pixels actually are. And that's the fragment shader. And those colors get up into the screen. So a vertex shader gets run every vertex. And a vertex shader handles stuff like camera movements, things like that. If the camera moves, now if you move your camera left, then all your vertices on the screen move right. Right. So the vertex shader transforms everything right when you move the camera left. And the vertex shader, after the vertex shader is run, hardware rasterization is basically turning triangles into pixels. And then those pixels get shaded, which means we have to figure out what color they are. And the fragment shader gets run for every pixel. And the fragment shader takes in stuff like position, texture, lighting, vertex color, all of these, and it outputs at RGBA. Right? That will be one fragment shader. Take all these inputs and output RGBA. This RGBA is shown on the screen. It's actually every potential pixel. That's why we call it a fragment, because when you have something, you have a wall in front of a wall, right? You could draw that wall first, and then that bit that gets overlapped actually gets calculated twice. But then it gets discarded because there was a wall in front of it. It gets the pixels of the wall can get covered by something that's closer. Can get covered by the pixel of another wall that's actually closer. So it's actually every potential pixel. But you can think of them as effective as pixels. So with this stuff, you can do some cool things. You can do some shader effects. The easiest meaningful thing you can do is function shading. So OpenGL defaults to per pixel, per vertex shading. It calculates lighting per vertex, and then it interpolates in the middle. With a fragment shader, you can turn this into function shading, in which it calculates things per pixel, which calculates light per pixel. And if you have bright speculators like that, you see vertex doesn't really do it justice. The OpenGL default pipeline, which is dead, but normal Gora shading doesn't quite do it just but with the shader you can customize whatever you want, and you can do this per pixel. You can also do fancy things like bump mapping. You can fake lighting to look like there is more polygons. You can add a lot of effects. You can also do stuff like cell shading, make the entire world look like it was a cartoon of some sort. And you can turn the Minecraft water into this if you run the shader, if you run a complex enough shader. One other thing you can do with fragment shaders is, or shaders in general, is something like post-processing. With post-processing, the idea is instead of rendering the scene to the screen, we render it into a texture first. We just tell Open GL, instead of rendering these triangles directly to the screen, set the destination to be a texture. And then what you can do is you can use this texture in another, as just any other texture. Right? You can slap this texture on the cube. You can slap this texture on a sphere. You can just use it as just any other old texture. And what you can do with this is, well, the simplest thing you can do with this is you render the screen onto a texture, and this texture is exactly the same resolution as your actual window, as your actual screen. And then the simplest thing you can do with this is just draw a full screen quad using that texture. Right. Just render it into a texture and draw that texture onto the screen. Now you've just done a whole load of nothing. But what you can do is you can apply a fragment shader to that quad, to that single quad that draws the screen. And what this fragment shader can do is it can customize it can look at multiple spots in the original screen shader. It can change it. You can do whatever you want to. You can make the screen brighter. You can desaturate the screen. Right? Just get the color of what was originally displayed on the screen. Get rid of the color and then output it. And then you will desaturate the screen. You can also do things like blur. Right? You can look at this screen, the fragment shader that's on the full screen quad. You can look at the texture around it, and then you can calculate some sort of average blur thing. And you can output that to the screen, and then you will get a blurred image of the other end. You can also do an effect called blue, which a lot of people hate actually. Notorious effect. Which is basically a blue, and then you add the blue image onto the original image, and you create a light halo effect. Can we do ambient occlusion as a post-processing? So remember, simplify AO for every point in your scene. Look for occluders in the hemisphere. Hemisphere, that's a direction. Look for occluders in front of you. So idea, the Open GL, we have the depth buffer, which is a buffer that already exists that handles ordering things. So the depth buffer is how Open GL handles closer things being in front of further away things. Can we read it and somehow get ambient occlusion of that? So run some sort of post-process full screen quad with a fragment shader that looks something like a blur, except instead of a blur, it looks around it and calculates ambient occlusion instead. Turns out, yes, we can. Surprise. And we run into a few complications. The first complication is we need to actually be able to read the depth as a texture inside a fragment shader. The second problem is that, as you can see, ambient occlusion is a pretty wide area of effect. Like a car here can affect ambient occlusion on the ground, right? Can occlude light on the ground. There's quite a wide range of. It's not very local, right? There's a big area that something potentially affects. So we have to sample in a large area. We have to read the depth buffer in a largish radius area for each pixel. And that can end up with speed problems. And also we need to learn the normal to know which hemisphere we actually care about. Now, first, reading the depth buffer. Here, to deal with reading the depth buffer, what you can do is you can actually tell Open GL to just say, okay, give me the depth buffer as a texture. You can actually do that. You can actually just, I think DirectX 11, the newer APIs, you can just read the depth buffer straight off from a shader instruction, from a shader command, shader function. So I don't like this personally. There are implementations that do this. I don't like it because I've run into encoding scheme differences and format loads where you ask the driver for a 24-bit depth buffer, and the driver goes, okay, here's a 24-bit depth buffer, all done. And then when you actually use it, you're like, this is not a 24-bit depth buffer. I've run into problems with that with certain drivers. And also encoding schemes. The drivers might have weird ways of encoding depth. It might not be linear. Like they might store the depth quadratically or something, or exponentially. They must store some power to it. And there's a reason for that. It's because they want to give more bits, or they want to give more precision to the things that are closer and further away. So it does make sense. But guessing what the driver does is annoying. So, which comes to the other way that I prefer, which is using a fragment shader that outputs the Z position, the vertex Z position, as in the R channel. You just render to a texture, except in the red channel, you just output the depth from the string, the vertex position Z. Now, you've got to be careful here. Also, one more thing here. Just before we go into these, so see how I'm actually outputting two textures at a time. I'm outputting two values. So you can actually do it. Okay. So a fragment shader can add up to like 8 or something. I think these days on more hardware, and it's way faster than drawing the entire thing twice, because that's what you would have to do using some of these. You have to render the entire thing, put it in one texture, and render the entire thing again for the depth. You can actually just use a fragment shader that just outputs to two different textures. So when we do this, when we install the depth, we've got to be careful, because the normal color, RGBA color, 16-bit color, 24-bit color, whatever, RGR goes up to goes from 0 to 255, right, 8 bits. And depth, you can have things very, very far away. Like if you're rendering like the sun or something, or like mountains, it can be much bigger, 255. Right? You can multiply by the value, but then you get step effects. You don't really get precision. So the easiest thing to solve that is just put that in just make a float, take texture, render to that. Okay. You can do that. Or you can use some sort of clever encoding scheme that does non-linear things, or spreads the position over multiple channels. Easiest way just to say, okay, that's float. Start using use a float texture for that. And there's good hardware support for that. So that's what a depth buffer texture looks like. Also, the things that are farther away have more depth. The things that are closer away have less depth. So now let's go on to the sampling bit. We got depth. Now we want to read depth in some meaningful way and get ambient occlusion. So what we want to do is we want to sample the area around the depth in front of us, looking for occluders. And one way, so let's first look at the sampling first before we look at the occluder part first. How do we sample? Sampling means reading off the texture, right? for every point, we need to look at the textures around us. So sort of, okay, I'm here, so I need to look sort of around me to look for occluders, to look for things that are in front of me, right, which will block my ambient light. So the easiest way to look around is just do two for loops, right? For every x, for every y in your box, read the texture at that point, right? So for every x, for every y, this is my current pixel. This is the position of my current pixel. For every x direction, every y direction, we look that way. We look at what the depth is there. We read the depth texture, which tells the depth at that point. Right? I'm here. I'm looking there. I want the depth of that compared to my depth, because that will tell me if that is blocking my ambient light. And then if it blocks my ambient light, then we add to some occlusion number, and then we divide by the total number of samples. Okay. Now this is too slow because this takes a lot of samples. It accesses the texture a lot of times. A better way to do this would be to sort of look in a circle or sphere, right? A sort of a virtual sphere, right? So, and this goes back into our into a circle sampling thing, where this looks more like the hemisphere thing that we're talking about, right? There. So, with a better way to do that would be sphere sampling, in which instead of sampling every single pixel in my neighborhood, I just sample a collection of pixels. Instead of sampling the depth at every single pixel around me, I just read someone. I just read some and just use that as the value. So let's say we take 16 samples. This sphere sample is just a table of an array of vectors which just store 3D directions in the sphere. Just random directions in a sphere, random vector directions in a sphere. And we add some random direction to our origin, and then we sample that. We read the depth at that. Right? So random direction, we read that. Random direction, read that. Random direction, read that. Do that for 16 minutes. So a random unit sphere. Something like that. Randomness of offsets. The problem with that is we're sampling here, right? Say this is our sampling pattern. And this is our current pixel. We sample here, these pixels here. When we move on to the next pixel, what we do is we sample there. And then the next pixel will sample there at the exact same pattern. Right? It uses the exact same pattern, hard-coded random pattern to sample ambient occlusion. So what you get here is you'll get a lot of noticeable patterns coming across. Right? You run into these weird patterns going across your screen because you've got the same sampling pattern across different pixels. So what you actually want to do is you want to actually randomize it per pixel. You want to shuffle it so that you get a random distribution per pixel. So what you want to do is you want to say you've got your unit sphere of random samples. You want to rotate that random per pixel. Okay. So rotating that randomly involves getting a random vector and then rotating your sphere sampling ball by that random vector. In this case, I use the reflect function. That's sort of like a cheapo way to shuffle a unit sphere along. So I get a random vector. I reflect my original sampling direction by that to get a new sampling direction. Now, to get this random vector, GLSL doesn't actually have a random function. So the common way to do random on GLSL is to use a random texture. Just Photoshop generate a noise texture and use that as your random function. Look up this random noise texture as some pixel UV-based, pixel position-based seed, right? This is the origin, which is the pixel X and Y position. It's multiplied by some random value. Look up the noise texture, and then interpret the RG and B channels of the noise texture as your random vector. Okay. So this will shuffle the sampling sphere every pixel to get much better random sampling. Now let's go to this occluder function. This is occluder function. This is sort of the meat of the entire talk. So this occluder, now we've got our sampling done. Given a sample and given ourselves our origin point P, we want to classify whether this point is blocking my ambient light or not. Right? So if this, say I'm here, right, and I sample here, if it turned out the depth of this sample is all the way somewhere like way over there, right? It won't really affect me at all. Right? It's way outside of my sampling sphere. I don't really care about it. So if it's here or something, way here, right? We don't care about it. It's something way over there, really, really far away, won't block my ambient light. So we ignore that. Okay, so that's the first check. Okay. The second check is checking the hemisphere. Right? If something is close to me but it's behind me, it won't really block my ambient light coming to me. Right? Ambient light's coming this way. If something like behind me, like here, I don't really care about it. Right? It doesn't really affect my lighting in any meaningful way. So we just ignore that sample. So this is now we're down to in the circle and in the hemisphere, in the right hemisphere. What we want to test here is if the sample is here, if my geometry looks like that, if the sample's here, or if the sample's here. Right? So basically, we're here we're at this point, we want to classify whether it's a green dot or a red dot. Right? Whether we found some open space or we found an occluder. Okay? And the way we do that is we look at the depth of the sample, which is SZ here. Say we're at this sample. So this is the camera. If you think about that's the depth buffer, and the camera is sort of looking down this way. That's where you are, right? That's the game scene, the depth of the game scene. So you expect this sample to be here, but when you read the depth buffer, it actually gives you something closer. This means that you found an occluder. You expect it to be here, and you expect it to be here, and you found something closer. So this isn't occluder here. You found a wall. So in this case, we return true. We found an occluder. If it's this case, we expect it to be here. We expect the sample point Z value to be here. But in actual fact, when we read the depth buffer, the depth actually gives us here. Then it is behind our expected value, and we found a green point. Right? Does this make sense? So that's that third check. Okay. Otherwise, classify as red. Okay. And here's a more visual representation. So of this. So the first check here will rule out some random point like here or nowhere. That's not inside our circle. The second point, the second check, if segment here, gets us in the right hemisphere that we care about. So this green hemisphere here. The third classifies whether these points are red or black. Right? Red is non-occluder, black is occluder. And the more occluders we have, the ratio of occluders to non-occluders will be our ambient occlusion. So now that's down. Where do we get the normal vector? We can sort of do a similar thing that we did to depth, and we just output it as a third texture. So we output the vertex normal vector in the XYZ in the RG and B channels of the texture. Okay. You've got to be careful because a texture goes from 0 to 255 or 0 to 1 GLSL, and a vector can actually face the other way. It can actually go to negative. So what you've got to do is you've got to sort of shift a vector that goes like that shift a vector that goes from 1, 1, 1 to negative 1, negative 1, negative 1 to sort of shift it to go from 0 to 1. That's what this times 0.5 plus 0.5 is doing. Okay? So we render to texture, outputting the normal as a texture. And it turns out you can just, instead of using 3 outputs, you can just reuse. You can just reuse that texture. Okay? You can just reuse that. Same thing. You can just reuse the RGB channels of this for the normal and the Z position for the depth. And this is a float texture, so a float texture is not negative value, so we don't have to do the times 0.5 thing. And this gets us something like this. Yeah. If you haven't noticed, that's actually quite noisy. Right? It sort of blotches and noises. It sort of looks like an old TV. Right? This is very noisy. So what do we do when we get noise? Blur it. Blur the entire thing, right? What we can do is we can render the SSAO into a texture. Right? Instead of rendering it to the screen, render that to a texture. So we first render it into the normal, the depth textures, and then we render the fragment shader using the draw full screen chord, render that into another texture. And then we apply a blur fragment shader to that texture. Now, what does a blur fragment shader look like? This is the easiest blur fragment shader. Okay? Just loop every X, loop every Y, average everything you see. Okay? So this gets run every pixel. This is a fragment shader. The hardware automatically runs at every pixel. So every pixel looks at its surrounding pixels and takes average. That'll give us a blur. The problem with this is exactly the problem we started with the sphere sampling view. What boxes that is too slow. We're taking way too many reads of the texture. So turns out, and also one more thing, we don't actually want to use the same technique that we use for SSAO here. We don't actually want to solve noise made by random sampling using more random sampling. That doesn't really solve our problem. We just introduce different noise. Turns out, fortunately, unlike SSAO, a blur is separable. What this means that you can first just blur it in the horizontal direction, and then blur the result of that in the vertical direction, and then you can prove that you get exactly the same result as if you did the entire 2D label for every pixel around. And this turns it from order of n squared samples into order of 2n samples per pixel. So this actually turns it from n cubed in the number of pixels to 2n squared in the number of pixels. So it's a pretty big speed up. So here's a visual representation. So we've got a single pixel. We first blur the pixel that way, and then we blur the result of that way, and we get mathematically the same result as full 2D. So that's what the fragment shader looks like to do that. So instead of having a nested loop, we have now 2 loops with an intermediate texture in the middle. We render to an intermediate texture, which is the U blurred only texture, which is this texture, intermediate texture, and then we blur that in the vertical direction. Okay. And here's our original noisy SSAO output from our SSAO shader. And here's what it looks like after blur. And here's original diffuse, just dull diffuse standard lighting, standard diffuse lighting with ambient tone. And here's our SSAO applied. Now let's take a closer look. Around these object edges, notice how we just introduced halos, right? Around the entire object, right? And also within the object. Across any edge, we now introduce halos everywhere. Why is that? The reason is because we can't just do a straightforward blur. What we're trying to do is blur the screen space ambient occlusion, not across the screen. We actually want to blur it. We don't want to blur it across the screen naively. We want to blur it across the surface of the object. Okay. Well, we can't actually blur it across the surface of the object, but we can make it look like we blurred it across the surface of the object. That's close. So, in order to make it look like that, we need to be aware of object edges. Right? We need to be aware of where the edges of where the object stops and where the boundaries of each. We need to understand something about the geometry. Across object surfaces, but not across object edges. So an easy way to do that is just read depth texture again. Right? You've got the depth texture there that you use for SSAO. You just read that, and you can just simply threshold it. Right? If the depth, so when you're blurring, or as you're taking samples, as you're blurring, if this sample, if the depth of this sample is too far off from where I am, you just ignore it for some random value of too far. Okay? And not only that, when something is further away, it's smaller on the screen. So we actually want to blur it less. Right? It has smaller features, so it appears smaller on the screen. And what we can do here is we can simply modify the radius of our blur per pixel depending on the depth. Just read the depth at the origin point and then just use that to modify how wide your blur is. And the blur width to getting blur width from depth is sort of like a little magic area. Here's a magic formula that I usually use, depending on the field of view and stuff. You can actually calculate it by converting the projection matrix by details. The magic formula that gets blur width on depth. And that's what the code for depth aware blur looks like. So it looks sort of like this shader, that shader, but with added. So now, instead of just reading the SSAO texture, we read the depth as well, the depth texture. And then if the depth difference is above some random threshold that we set, then we ignore it. Otherwise, we take this setting into account. And also modify the blur width by S, which is our magic blur width. So here's the original straightforward dumb blurred SSAO. Here's what it looks like with edge with object aware blur. So just go back here. So that's just a straightforward blur across the screen. Here's object aware. And here's the original halo effect. So confronting on the halos around here. And here's the halos by using object aware blur. And that's it. Simply multiply the SSAO with the original scene. So here's an overview of this rather simple method. So have your scene geometry, the scene shader, outputs the normal diffuse color, the normals, the depth buffer. These two textures can be the same texture if you really want. You run SSAO, calculate the ambient occlusion. This gives you a noisy ambient occlusion texture. And you blur in the U direction, the intermediate texture, and in the V direction. Notice how the blurs take the depth buffering as well as the ambient occlusion texture, because you need to be object aware. And then that gives you the final SSAO texture, which you combine with your existing scene. And that actually updates the scene. Here's the normals of what a scene looks like, example. So the RG, the X Y and Z channels on the normal are being rendered to RGB channels. Here's what the depth buffer will look like. Here's what the ambient occlusion will look like for such a scene. Here's what the ambient lighting, just constant white lighting everywhere with texture. And here's ambient